Hey guys, this is me. Nice to see you. Hope you guys are doing well. I'm sure you're all stressed about this final. I know I am, which is kind of why I want to do this. The reason why I'm doing this is because I find the best way to know if you understand a concept is if you're able to explain it to someone else. So that's what I'm trying to do right now. Explain sort of the base concepts to you guys. Like I should clarify, this isn't like a how to find numbers video. It's not even a very advanced tutorial. It's just very basic concepts and whatnot because I feel like the math is way harder if you don't know what the numbers mean. I feel like most of us don't know what the numbers mean. So I've attached in the description of this video a PDF of all the notes I've taken. If you want to get more detailed into what you should be looking for, go there. That's all there. If you want to learn more about numbers, ask Ryan in our group chat. Um, Ryan, I'm sure you don't mind. Sorry if you do. But Ryan's a total math wizard, better than I am, which is amazing to me. He's quite the numbers guy. So if you guys have questions about that stuff, ask Ryan. This is basic concepts because I feel like it's so hard to understand that sometimes because we can't even see what's going on. So I'm going to kind of try to follow sort of the notes I have so far, but for the most part, I'm just kind of going to go on my own little rant and whatnot. What I really want to do for you guys is not so much to create a giant robot of physics with all these detailed little parts and whatnot, more than I want to just tell you guys an overall story or an overall painting. If I can do that, then I think we'll be in pretty good shape. So ideally, this video will be under 10 minutes long, so we'll see how that goes. But chapter 21, right? So here's what we learn in chapter 21. One of the first big things that we learn is the law of conservation of electric charge, which basically says that charges act a lot like energy. You have positive charges, and you have negative charges, protons and electrons, which, by the way, those have the same magnitude of charge, but they're different signs. Electrons are negative, protons are positive, and those use something called an elementary charge, which I'll go into a little bit later. But the law of conservation of electric charge basically says you cannot create or destroy charge. You can only transfer it. So if you want to make an object more positive, you have to either get some of the negative out of there and move it somewhere else, or you have to take positive from somewhere else and move more of it into there. You can't just create more positive, you have to get it from somewhere. Sort of like you can't just, create or have wood, you have to chop down a tree to get it. Same thing with electric charge, same thing with energy. Now, one of the nice things about this is that it kind of makes the idea of, well, that's sort of the basis of the idea of, like charges repel and different charges attract. But why does that happen? Why are these attracting? Why are these repelling? It's because it has to be because, quite frankly, there are forces happening between these two things. There's attractive forces and repelling forces. That's what Coulomb's law tells us. Coulomb, this smart motherfucker, basically figured out, hey, a force that one charge is putting on another is equal to the magnitude or the size of the charges and how far apart they are. So how big they are, how far apart they are. Like that. So that's what Coulomb's law tells us. But it's sort of the same problem with gravity, right? Because we know that there's a force of gravity, but it's kind of hard to see like what that even means, right? Like, is gravity the same on this level as it is like another on the way up on Mount Everest or something, or all the way up in space? Obviously, you guys know that no, gravity is not the same. It's changing, right? Like it's a force at this level that is this much, but the further away you get from it, the weaker it gets. And the closer you are to other planets with stronger gravities, the stronger their gravity gets. So that's why we have something called gravitational fields that shows us, how strong is gravity when we're this close, and then this far, and then this far, and so on and so forth. We have something just like that for electric charges. And that is known as the electric field, which is 21-6, by the way. Coulomb's law is 21-5. This electric field is 21-6 and all through 21-8. But the electric field is the exact same way. The logic behind it is you'd have like a giant source charge, right? Let's say this is positive Q. Now you have a teeny tiny little test charge. It's a point charge. Its size is so tiny it doesn't even matter. All that we really care about is basically the sign. Let's say that this is a positive one. What is the force that this thing is imposing on this from like this distance? What does that look like? What does it look like here, or even here? How powerful is that force? And the equation for that is that the electric field is equal to force over unit charge. It's basically just figuring out, so basically charges are creating fields, and that's exerting a specific force, which again, those forces are dependent on the magnitude of the source charge and the distance between them, which is r in those equations. So that's three big things we have right there. And that's pretty much the hugest stuff you're going to find in chapter 21. It's that, one, charge cannot be created or destroyed, only conserved or transferred. Two, those charges create forces which can be measured, and it's based off of how big the charges are and how far apart they are. And three, you now know that electricity acts a lot like gravity, where it has its own field, and you can test that by just doing tiny little, basically non-existing points and seeing what forces would act on them. That's how that works. And that's what you're going to find in chapter 21. Chapter 22 talks about flux, Gauss's law, and yeah, it's important, but in terms of painting the overall picture, it's not that important yet, but I'm still going to go over it, obviously. So chapter 22 talks about the electric flux, and that's what electric flux is basically how much electric field is passing through a given area, right? Like in the same way that speed is just distance over time, flux is electric field over area. And the thing about that is that you need the electric field to be perpendicular to the area, just so that the math adds out that way. Or, yeah, around perpendicular. If it's not perpendicular, that's where that cosine theta comes in, where theta is the angle between those two things. And what's really nice about it, though, is that it gives us this very important thing called Gauss's law. And I even started here because it's that important. Because the equation is the integral of E times dA, which is equal to Q enclosed over epsilon naught, which is a total fucking gibberish, and half of you guys probably don't understand what that means. And I want to tell you that that's okay. I'm about to explain it. So the integral of E dot dA, what that basically translates to is, hey, what is the amount of electric field over a closed area? That's what that little, what looks like an elongated S with a circle through it is saying. It's saying that, hey, we're doing a calculation through a closed and enclosed area, which is the A right there. And I'm sure most of you guys know how to do integrals, so you would know that this is equal to, the integral of this is E times A if the area is constant, which for this law you kind of want it to be. Q enclosed is basically the charge inside of that area, and epsilon naught is just another constant. Now, the nice thing about Gauss's law is that it tells you the flux for an overall area just by using very simple shapes and whatnot. Like, for example, the area, if you want to find the flux going throughout a sphere, you would just use the surface area of a sphere. And I even give that example in there. You would have E is equal to Q over 4 pi epsilon naught r squared as your final answer for the electric field. And since you now know what the electric field is, you could figure out, what the, you could also figure out what the flux is. But more importantly, you can find the electric field just by knowing the area of what you're looking at and the charge inside of it. So that's really important, right? Now you can figure out how forces are measured, and you didn't even have to really look at all these crazy charges. You just had to look at, hey, what is the area? What's the charge inside of it? It's a really useful tool. And the nice thing is that there's actually an example I give in here where flux through one area is the same as flux through another area. So look at that. That's a really good example of how just very simple logic can make things like this way easier. But anyway, we're already over 10 minutes, and I feel like I'm kind of getting a bit too picky in some of these areas, so I'm going to try and pick it up a little bit, because now we are in chapter 23. This is the biggest son of a bitch you guys probably faced when you first saw this, right? Because chapter 23 talked about electric potential energy. It talked about electric potential, and then it also talked about potential difference. And you can't even tell what the difference between any of those is sometimes. It's absolutely ridiculous. And the book really doesn't, in my opinion, it didn't do quite as good of a job as I would have wanted it to when it comes to explaining this. Because when I figured out what this actually was, it was so much easier than what I thought. So I'm going to explain that right now, right? So there's three things that chapter 23 talks about: electric potential energy, electric potential, and potential difference. Now, electric fields are nice, right? They tell us the force put out on certain charges just by knowing a few very quick variables, and you can find that for any distance away. Super useful tool, but we also found out earlier that, hey, electricity is its own sort of energy. Why can't we apply conservation of energy there? And those numbers actually end up being way easier, so why don't we try and figure that out? And what they figured out was they basically tried to define electric potential energy, which is basically just the amount of work you're doing on something. Because, quite frankly, yes, particles have potential energy. When you have two positive particles like this, they're going to repel each other like crazy, and that's going to be kinetic energy. They're going to be going everywhere, leaving you with just potential energy right before they do that. So they figured out what that was. They said, okay, it's equal to charge times the electric field times the distance between them. And that's an equation that I've given that for, and that's for a uniform electric field. So that part's easy enough, right? Electric potential energy is just like regular potential energy. It's the exact same thing. Electric potential is slightly different. Electric potential has the same relationship to potential energy, the same relationship that electric fields have to force, right? The electric field tells you how much force is possible in a given point. Potential energy is electric potential is the same way. It tells you how much potential energy is possible where you are. Weirdly enough, you could consider it the electric potential to be the potential of potential energy. It's what's possible. So let's consider an example, right? Let's say that you've got two plates, right? One is positively charged, one is negatively charged. And you've got a positive charge on that positive wall right now, and you're going to have that go to the negative wall. Well, at the start, we've got a high U. U is a symbol for potential energy, by the way. So at first it's high, very high, and then it goes into low because, boom, it repels, boom, 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 fast, 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 and then boom. It's over here now, low potential energy. Now you might be thinking, well, hold on now. Shouldn't it have a lot of high potential energy? Because now that it's just stuck to the negatives, that means that it has potential to go really fast, right? It doesn't actually, because remember, like charges attract, and potential energy is equal to the work done on it. That's something I talk about in my notes. Potential energy is equal to how much work you're doing on this. So you have to do a lot of work to pull this apart. And it's only when you're pulling this positive apart from the negative that you're doing any work on it. So then you have potential energy, but then you let it go, it's just going to go right back. So you don't have any potential energy, funnily enough, until you start moving it. Electricity is kind of acts backwards that way. That's how it works. Now the nice thing is that electric potential is really easy to understand that way. And the symbol for electric potential, by the way, is V. Potential energy is U, potential itself is just V. At the start, you have high potential for potential energy. And then once you have low potential energy, you have low potential. This makes sense, right? This is how positive molecules work. Now, the important thing to remember is that potential follows the exact same lines as the electric field lines. Now I'm going to show you the part where you guys probably got the most confused. Oh, hang on. I got to do the symbols again. Boom, 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 boom. Here we go, right? So the negative, you would think, oh, it's got a lot of high potential energy when it's with like charges. So that means it has high potential, right? And then it's going to low potential and low potential energy. You're half right. And this was the most confusing thing to me when I was trying to learn this. And I'm about to blow your minds with how easy it is to sort of visualize this. Boom. Your actual negative molecules go from low potential to high potential. Positive molecules go from high potential to low potential. Now you're probably thinking, what the hell does that mean? You just said that potential is directly related to potential energy, or how much of that is possible. This is going the exact opposite way. Why does this make sense? It's the same reason why you don't switch directions for electric fields based on the sign of the particle. You need standards for that math, but in the end, the vocabulary just becomes really confusing. So yes, this is still losing all its potential energy when it gets to the attractive positive. It's just that the words are different. And a really good way to think about it is this, right? Let's say you're going on a road trip, right? You're getting in your car, you're going to go down south to see your family or something. Let's say you're a positive molecule, and your home is another positive molecule, like this. Here's your home, here's you. Here's where you're going. It's a negative place, or it's a negative molecule. So home is positive, destination is negative. And if there's in-laws and every type of family there, it is kind of a negative. So you're traveling, and then boom, you're there. You went from home to destination. High potential to low potential. Makes sense. But now you've switched teams, right? It's time to go back home, so you go from positive to negative. And this is still negative though, right? This is your destination. You're still going to say, oh, I'm going from my destination to home. It's low potential to high potential. High and low potential are just like destination and home. They are standards. They don't really change like that. That's why they keep their names. That's why this confused you, because this wasn't explained properly. And of course it confused you. You should think that it would be relative like that, but it's not. They have to keep standards like this so that every other scientist with big brains doesn't feel so confused, but in a weird way just creates more confusion. But that's how it works. Think of it like a roadmap. And that's a really good idea for physics in general. Think of it in simple terms. Otherwise, you're just going to get so confused. But anyway, so that's the difference between electric potential energy, electric potential, and potential difference is basically, oh, how much potential did you have and how much do you have now? It's the change in potential. That's all it is. Now, you're probably wondering, okay, fine, we understand all that now. That was painful, but we get it. Why does knowing potential and potential difference matter? That's explained in chapter 24. Chapter 24 is where everything comes together. So here's our building blocks, right? We've got that charges are conserved. We know they create forces. We can measure those forces. We can find out the energy from those forces. And we can measure those energies by using potential and potential difference. This is where it all comes into the world of electronics. Chapter 24 talks about capacitors. These are devices that store that electric charge, and they normally consist of two plates, right? Just like this, actually. One plate's positive, one plate's negative. A really good way to think about potential energy is that it is storing energy, right? It is storing energy so that you can use it for all these crazy moving arounds later. That's how it works. And it's the same thing with electricity. It's how batteries work. They are storing energy so that your computer can use it for when you turn it on, and you can just mine away your obsidian and ignore your taxes like every other good American out there. That's how it works, right? But how do you know how much energy you got? Potential difference. That's what it is. Potential difference tells you, oh, what's the difference in your electric potential? And your electric potential is telling you what was the potential energy you even could possibly use. That's how it works. That's why this is so important. That's why it's amazing that these charges are creating forces, because it tells you that there's energy. That energy tells you that, hey, there's energy you can store to make batteries and really cool things. Now, the way that capacitors work, though, is they basically, so what we just did, just a little second ago, I'm going to try and switch this around again, was we basically said that positive molecules go from high potential to low potential, naturally. This is trying to do the exact opposite, actually. Instead of making our positive molecules go from high potential to low potential, we're trying to make it so that these positive molecules are now going from low potential to high potential. And by the way, from here on out, you can think of potential difference as voltage, because that's basically what it is. It's a measure of how much energy or volts you're getting. This is what a capacitor is doing. It's saying, hey, take this and move it to here. And you're probably thinking, why on earth would you do that? That's just making more potential energy. And that's exactly why you're doing it. Because potential energy means there's more energy for you to store in your battery. So now you've got more energy to work with later. Now, at first, this is really easy for the capacitor, because before the battery is turned on, which is where the potential difference comes in, as in where energy is coming from, the flow of energy, the plates are neutral at first. It's not negative and positive, it's just neutral. Then it's turned on. And at first, it's super easy because, oh, you're just taking positives and you're putting them on the other plate. But then, over time, this wall becomes more positive. This wall becomes more negative. And it's taking a lot more work to get this tiny little thing to fit in there. It'd be like trying to take a million tiny, tiny little magnets and fitting them all inside your suitcase. It's possible. Of course it is. But it's still a lot of work, especially when they're all trying to fight each other. That's why you need a lot of work or a lot of energy to make this work. And that's what's so interesting about the technology. Now, again, there's two different ways to do this. There's parallel and then there's series. And I go into the math and sort of try to explain that in my notes. I also talk about the storage a little bit. Dielectrics, that's basically a material you put in between the plates to increase that process, make it so you can get them even tighter together. Stuff like that. I could go into all the numbers if I wanted to, but we already have a teacher who is doing that, and that can be real tiring some days. So I just want to give you guys the basic tools. So I'm going to try and paint this picture for you guys one more time, and if this has been the worst lecture you've ever heard, I'm really sorry. I tried. I'm really sorry, though. But I really hope this helps. But anyway, charge is conserved. Those charges create forces, which we measure, which we found through Coulomb's law. We found how those forces diminish over distance with electric field lines. And electric field lines go from positive to negative. Well, we then found out that charges act a lot like energy. They have energy. So we figured out that potential energy, right? And we figured out that, so we came up with three terms for energy. Electric potential energy, which is like regular potential energy. Two positive molecules are going to have a lot of potential energy because they're going to go flying off. Electric potential, is basically the measure of that potential energy. It's the electric field for that energy, and it goes in the same direction as the electric field too. And then potential difference is basically the change in that electric potential. And it's really important to remember that the direction of those fields don't change based on the charge. That's why electric fields are always from positive to negative, and that is why it's always high potential to low potential, and that's why negatives are always doing the opposite. They're not broken, they're just following standards, even though it's really confusing. Think of it like a roadmap. You're going home to your destination, and you're going to your destination from home. You're going high to low, low to high. High to low is for positive, low to high is for negative. And the really nice thing about this is that this potential difference is basically a measure of how much energy storage you're getting. And that's using things like capacitors and batteries. It's why batteries take so long to charge, because you're having to place more and more charges going against their potential where they want to go. Positive molecules want to go from high to low potential, as in they want to move around a lot. Making them do the opposite means that there's more energy to use later. That's the picture right there. Charges create forces. Forces involve energy. Energy can be utilized to our advantage in electronics. That's how it works. And I really hope that helps you guys. I know I was kind of rambling on a bit. Consider this a test, right? This might not be where I go with the rest of the chapters, but if you guys liked how this went, if you guys enjoyed the content or at least found it to be educational, please tell me, give me feedback in the group chat that we're in. If you really like it, I will do more of them. If you guys hate it, I won't. I'll just leave it alone. But yeah, I really hope that helps. Again, this is just for basic concepts. I want to be able to tell you guys the story, and then you guys are going to be able to, you guys are smart enough to do the research for the numbers on your own. I have faith in that. I think it's just really hard to understand why the numbers are what they are. And if I helped even a little bit in that sense, then that means that the video was a success. Either way, though, I hope you guys have a fantastic day. I'm going to be doing this every day, pretty much. Maybe not the videos, but I'm taking these notes every day. So if you ever just need someone to like cross-reference with, hit me up. I'll do what I can. Anyway, love all you guys. Good luck in the final. See you tomorrow. That kiss was weird. I don't know why I did that. It's because I was just putting my other sibling to bed, and like I kissed them goodnight. They're sweethearts. All right. Anyway, see you guys tomorrow. Peace out.